Alright, welcome back. This is Module 10, Chapter 7, Part 1. So this one's going to be slightly different, this video, because I want to show some drawings and so forth, and so you'll notice this video is slightly different. So this chapter really deals with the periodic table of the elements. And if you remember, we talked about a mole, and really a mole is a chemist's best friend. But the periodic table is actually one of the most significant tools that a chemist can use that helps organize and recall chemical facts. So the periodic table really arose from the periodic patterns in the electron configuration of the elements. So the trends within a row or a column form patterns that help us make predictions about chemical properties and reactivity. And so elements in the same column will contain the same number of outer shell electrons, or what we call valence electrons. Alright, so really this whole Chapter 7 is trends of the periodic table, okay, which I like to call a cheat sheet for chemists. And we're going to focus on three major trends, which is the size of atoms and ions, ionization energy, and electron affinity. Okay? And so a key principle in understanding the properties of atoms depends on electron configuration and how strongly the outer electrons are attracted to the nucleus. Okay? So I really want you to make sure that you remember this part. Alright, so when we talk about these trends of the periodic table, one of the things that we should note is as principal quantum number, which is called n, increases, the atomic orbitals become larger and less stable. Okay? And as the number of protons increase, any given orbital becomes smaller and more stable. Okay? And these two rules are really going to help us remember and apply to how effective nuclear charge changes. So you should definitely remember that we have periods shown here, right, which go across, and most of these principal quantum numbers are kind of pretty much you can follow just the number on the period. And then we have our groups which go down. Okay, and each group has the same number of valence electrons in each one. Okay, where group 8A are noble gases and have a complete valence shell electrons. Alright, so a large majority of the properties of atoms depends on electron configuration and how strongly the outer electrons are attracted to the nucleus. So really to understand effective nuclear charge, we need to understand what's called Coulombs Law. Okay? And it describes the strength of an interaction between two electrical charges. And these are usually the nucleus and the electrons. Okay? Electrons are negatively charged and the nucleus has protons and neutrons. Well, the protons have this positive charge. Okay, and so if we know we have two electrical charges opposite, they're going to attract one another. Okay, and Coulomb's law just says the strength of that interaction really depends on both the magnitude of the charges and the distance between the two. So as the nuclear charge increases, so as it becomes more positive, the force is going to increase. Okay, and if the electrons move farther from the nucleus, then the force is going to decrease. So if you think of an atom that has many electrons, then you can realize that the electrons are going to be attracted to that nucleus, right? Because that means it has a lot of protons, and so that negative charge is attracted to the positive charge. But at the same time, these electrons, the farther they are out, the more they are being repelled by the electrons surrounding it. Okay? So it's kind of a give and take relationship. And so the nuclear charge that an electron experiences is really dependent on both factors. So when we talk about the effective nuclear charge, we mean that it's the charge that's experienced by an electron on a many electron atom. Okay? And we can also define the effective nuclear charge with the equation, which is given here, which just says the effective nuclear charge, which is abbreviated capital Z with EFF, is equal to just the atomic number Z minus the screening constant. Okay? And the screening constant we can kind of think of more of just the core electrons, so the inner electrons. And so if we look at the figure shown here, we can see that if we look at sodium, the nucleus has 11 protons. So this little bit in here has 11 protons. We have 3 valence electrons, right? And it has a total of 11 electrons, which are attracted to this positively charged nucleus. So you can kind of feel those are just kind of being pulled in. Okay. Now the sodium atom contains 10 core electrons, right? And it just has this one electron in this valence electron shell. Okay. And so these 10 electrons inside are kind of screening this one valence electron from that positive charge. So we can take a look at this a little more detailed. Okay, so now we're going to take a look at some different atoms and look at the size and shape accordingly. So we can first look at like a sodium atom. Okay, so sodium we know has 11 electrons. Okay, so sodium has 11 electrons. And so if we draw the atom for sodium, okay, we can draw our nucleus and we can put in 11 plus charges, which are 11 protons. Okay, and then we're going to have our electron shells. And so if we think about sodium, we know that we have a total of 11 electrons. We look at sodium and it's in the period 3, which means it has n equals 1, n equals 2, and n equals 3. Okay, so if n equals 1, that means that L must be equal to 0, right, because L is equal to n minus 1. Which means that a 0 means that we have the S subshell, which holds a total of 2 electrons. Sodium then has an n equals 2 shell, which means that it has L equals 0 and L equals 1. Okay, which means that we have an S and a P subshell. The S subshell will hold a total of 2 electrons, and the P subshell will hold a total of 6 electrons, 3 in each of the P subshells. So PX, PY, and PZ each hold 2, for a total of 6. We then have the n equals 3 subshell, which means that L equals 0, 1, and 2, which means that we have an S, a P, and a D orbital, which means that this can hold a total of 18 electrons, 10 in the D, 6 in the P, and 2 in the S. And so we can draw in our 11 electrons accordingly. So first we can draw our n equals 1 subshell. Okay, and we can put in our 2 electrons, which we know sodium has, right? Because that is 1, then our second. So then we can draw our n equals 2 subshell. Okay, so this is n equals 2. And basically our next 2 electrons, right, the lithium and the beryllium, are going to go in the S orbital. But for simplicity, we're going to draw all the S and the P and everything in the same subshell. Okay, so if we look at sodium, we still have all these P orbitals that need to be filled. So we add 6 more for a total of 8 electrons in the n equals 2 subshell. Right, so we have our 8 electrons there. Well, then we go to the n equals 3. At this point, we've placed 10 of our 11 electrons. So in the n equals 3 subshell, we have 1 electron left, and we can put that into this n equals 3 subshell. Alright, so when we're talking about effective nuclear charge, we're looking at the charge on the valence electrons. Well, sodium has 1 valence electron. It has 1 electron in the outermost shell, okay, in the n equals 3. So you can think of this electron as, when we think about the effective nuclear charge, it's being attracted to this positively charged nucleus. Okay? At the same time, there's other electrons around here that all have these negative charges, okay, which are kind of repelling this electron as well. And so we can count these core electrons, the ones that are in this, n equals 1, n equals 2, as shielding electrons. They shield this valence electron from the positive charge in the nucleus. And so if we calculate our effective nuclear charge, so Z EFF is going to be equal to Z minus the screening, which means that our atomic number is 11 minus our screening constant, or screening number of electron, which is a total of 10. So all the screening electrons are in the n equals 1, n equals 2 for this particular atom. And so we have a +1 effective, effective nuclear charge on that atom, or on that electron. Alright, so if we take sodium and then we can look at another, we could go to magnesium. And so If we turn to magnesium, okay, and so here we're talking about magnesium, okay, once again we can draw our entire atom, okay. Magnesium has an atomic number of 12, which means it has 12 protons and 12 electrons. So we can draw our nucleus, we can put in our 12 charges. So there's 12 positive charges in there. And then we can start filling our electron shells. So we first have the n equals 1 subshell. Okay, we're going to have an n equals 2 subshell. And we're going to have an n equals 3 subshell. Okay, and if we put these electrons in, as we would have with the last, okay, so we're going to have 2 in the n equals 1 because the 1s can only hold 2. Then we go to n equals 2, which can hold 2 in the s, 6 in the p for a total of 8. Okay, then we still have, that's a total of 10 electrons, we still have 2 left. Okay, and so at this point we can say, alright, well how many valence electrons do we have? Well, we have 2, right? Because in the outermost shell we have 1 electron here and 1 electron here. So our core electrons are the 10 that we have that make up the n equals 1 and the n equals 2 subshell, so a total of 10. And so if we calculate the effective nuclear charge, we can say that 12, which is our atomic number, minus 10 is equal to plus 2. Alright, and so what we notice is that the shielding stays the same, but the atomic number is increasing, okay, across the period. And so because of this atomic charge in the nucleus, you can think of this nuclear charge is getting stronger and stronger in the center. And these electrons, although we're adding more electrons, they're more spread out, right? And so these are actually being attracted even more so by this increase in positive charge. And so an effective nuclear charge is going to increase as you move across from left to right of the periodic table. Okay. One of the other things to note is the size of the atom, okay? As you add electrons in these different shells, okay? So as we're adding electrons out here, what happens is these electrons are strongly attracted to the nucleus, right, by the effective nuclear charge. If it's increasing as we move across, as we add electrons and protons, they're being more attracted to the nucleus, and therefore the size of atoms is going to decrease as we move from left to right as well in the periodic table. So if we were to compare this magnesium to sodium, okay, if we drew sodium here, we would have sodium, okay, and then we would have our n equals 1, our n equals 2, our n equals 3, okay, so it should be much larger, or a little bit larger. We could also draw sulfur, okay, if we draw sulfur, which is farther on the periodic table, it's 16, so it has a total of 16 protons and 16 electrons. So let's draw sulfur. Okay, we're going to have our 16 positive charges in the nucleus, and then we can draw our electron shells. So we're going to have our n equals 1, our n equals 2, and our n equals 3. And you'll notice I drew it a lot smaller because what's happening is we have our 2 electrons in the n equals 1, we have 8 in the n equals 2, and then we still have a total of 6 more electrons that can go into the n equals 3. Okay, and so all these electrons, because we only had 2 electrons in this outer shell in magnesium, but in sulfur we have 4 more outer shell electrons in the valence shell. And so each one of these are then being attracted more so to this nucleus. And so it basically sucks everything in. Okay, as you move down the periodic table for something like potassium, okay, we can take a look at this also, where we basically have a total of 19 protons and 19 electrons. Okay, and if we draw these electron shells, we're going to have the n equals 1, the n equals 2, the n equals 3, and then we even have an n equals 4, okay, which is going to make potassium actually larger than sodium as well. Okay, so we put 2 in the 1s, we're going to put 8 in the 2, so this is the 2s and the 2p, 1, 2, 3, 4, 5, 6, 7, 8. Then we're going to the 3, which can actually hold a total of 18 electrons because it has an s, a p, and a d orbital. But if we go ahead and put our first 10 in, or sorry, if we put in our first 8, right, to fill the S and the P, okay, if you remember, we're going to fill the 4s too before we fill the 3d based on the periodic table. And so our one other electron is just going to go in this 4s. And so it's important to understand not only the size of the atoms, but also the effective nuclear charge. So we could also calculate the effective nuclear charge of the sulfur, which is going to be 16 minus 10, which gives a plus 6 effective nuclear charge on those valence electrons, right? And that's why they're more attracted to the nucleus, so they kind of get smaller. And for potassium, we have a ZF, which is equal to 19 minus the inner electrons, which is 18, which is equal to plus 1, okay? Which is the same as the sodium, but because you go down, okay, the electron cloud is more diffused, okay? So electron repulsions are more spread out, which is going to lead to an increase in the effective nuclear charge.